All right, welcome to the explainer. Ever wonder what really turns a simple piece of code, something that just works, into professional, robust software? Well, it's not magic. It's all about design. Today, we're going to break down the foundational principles, the absolute bedrock of great software engineering.
So, what is that difference? I mean, really, it's not just about making sure the code runs without crashing, it's about something bigger: architecture. You see, expert developers, they have this secret blueprint they use. It's what we call the 4 pillars of object-oriented programming, and it's how they build software that's meant to last. Now, it's really important to not think of these as, strict, rigid rules you have to follow. Think of them more like the actual architectural pillars that hold up a building. If you get these pillars right, you're building software that's not just functional, but also secure, simple, reusable, and flexible enough to change and grow over time. Okay, to make all of this really concrete and easy to understand, we're going to stick with one simple analogy for this entire explainer: a bank account system. Seriously, it's the perfect way to see these sometimes abstract ideas in action. All right, pillar number 1. So if we're building a bank account system, what's the absolute first thing we need to worry about? Well, it's got to be protecting the data, right? We have to protect that account balance from, honest mistakes or even somebody trying to misuse it. And that brings us right to our very first pillar. And this pillar is called encapsulation. Basically, think of it like building a secure vault for your data. What we do is we bundle the data, like the account balance, together with the only methods, the only ways you're allowed to touch that data. Things like deposit or withdraw. This makes it totally impossible for some other random part of the code to just reach in and mess with the balance. It's all locked down. And you know what? This code snippet here shows the difference perfectly. Just look at the left. See that public keyword? That means the balance is completely exposed. It's wide open. Any other part of the program could just reach in and set it to whatever, $1 million, -50. There are no rules. But now look at the right. By making that balance private, we've locked the vault. The only way to change it is by using our controlled methods, deposit and withdraw. And inside those methods, we can add logic, right? We can say, nope, you can't withdraw more money than you have. That is security. That's encapsulation in action. Okay, so our data is safe. It's locked away in its vault. Awesome. But a secure system isn't very useful if it's incredibly complicated to actually use, right? So how do we give the user a simple, clean interface without, showing them all the messy, complex stuff happening in the background? Well, that is the job of our second pillar, abstraction. I love this one. You can think of it as the need-to-know principle. It's all about hiding the complexity. We show the user only the essential features they need, while all the complicated machinery just does its thing, completely hidden from view. And a real-world ATM is the absolute perfect example of abstraction in action. Think about it. When you walk up to an ATM, you have a very simple set of steps, right? You insert your card, you type your PIN, you pick an amount, and you get your cash. You don't know, and you definitely don't need to know, how it's securely connecting to the bank's network, or the mechanics of how it counts the bills, or how it's checking your balance in a database. All of that complexity is completely hidden. That is brilliant abstraction. All right, so our first 2 pillars gave us a system that's both secure and simple to use. That's great. But what happens when the business comes back and says, hey, we want to offer new kinds of accounts, like a savings account or a business account? This is where our next 2 pillars come in. And they kind of work together as a team to solve this exact problem: how to make our software grow and adapt without having to tear it all down and start over. So the first part of this dynamic duo is inheritance. This is a really powerful idea. It lets us create a kind of master blueprint. Let's call it a generic account. This blueprint has all the basic stuff every account needs, like a balance, a deposit method, a withdraw method. Then, when we need to create new, more specific types of accounts, we don't start from scratch. We just inherit from that original blueprint. So, for example, we can have a savings account and a checking account that both inherit all the core features from that main account blueprint. This is absolutely huge for reusability. We don't have to write the code for deposit and withdraw over and over again. We get it for free. We just add the little bits that are unique, like, say, an add interest method for the savings account. Okay, so this whole concept of building from a shared blueprint, it unlocks our fourth and final pillar, which is called polymorphism. Now that sounds like a complicated word, but it literally just means many forms. And it's what makes all this inherited code so incredibly flexible. So what does many forms actually mean when we're writing code? Check this out. Polymorphism lets our program treat a very specific object, like a savings account, as if it were just a generic account. Now, why is that a superpower? Well, imagine you have a list with all different kinds of accounts in it. Savings, checking, whatever. You can write one single piece of code that says, hey, go through this list and calculate the end-of-month fees for every account. And it just works. It doesn't care what kind of account it is. It can handle any new account type we dream up in the future without us having to change that one line of code. It's incredibly powerful.
Okay, so there you have it, our 4 pillars: encapsulation, abstraction, inheritance, and polymorphism. Now let's just take a step back and see how they all work together, how they support our entire bank account system.
This table really sums it up perfectly. Encapsulation is our secure vault, locking down the balance. Abstraction is that simple, easy-to-use ATM interface. Inheritance gives us those reusable blueprints for things like savings and checking accounts. And finally, polymorphism is the magic that lets us treat all these different account types in one consistent, flexible way. See how they all build on each other?
So, what's the big takeaway here? What does all this mean for you when you sit down to write your next piece of software? Why should you even care about these pillars? Because honestly, using these pillars is a fundamental shift in how you think. You stop just writing code that solves the problem for today, and you start designing an architecture that's built to last, that can adapt to whatever comes tomorrow. Your software becomes secure because of encapsulation, simple to use because of abstraction, reusable because of inheritance, and super flexible because of polymorphism. You're not just a coder anymore, you're an engineer, an architect. So, the next time you fire up your code editor, I want you to ask yourself this one question. Are you just laying bricks, solving one little problem at a time? Or are you designing the whole building, thinking about the future? Because adopting that architect's mindset, well, that's the first real step to building truly great software.